Okay. So yes, my name is Milena Guevara-Bertsch. I did my PhD in the quantum optics and spectroscopy group of Rainer Blatt. I did my PhD in an experiment more related to the work that you do. So I work in a clock experiment. So I was doing quantum logic spectroscopy with calcium and aluminum ions. But now I'm doing a postdoc under the supervision of Thomas Mons. And this one is more focused on quantum computation with trapped ions. So I was asked to give a broad audience talk about quantum computation and and simulations with trapped ions for a broad audience. So I hope I can make it both interesting and clear for everybody. I was not completely sure how broad I had to make it, so I made it quite simple from the beginning, and I slowly start to build up. So I hope what you get is like an idea of what you can do in the sense of quantum computation and simulations, especially with trapped ions. Okay. It was working and now it's not working. Oh. Okay, now it worked. Okay, so for those who don't know Innsbruck, this is a bit how it looks in the winter. It's extremely nice. So if you haven't been there, I would fully recommend you to visit. It's amazing if you know how to ski or snowboard, but it's also very beautiful even if you don't know, to walk a bit in the mountains and nature. It's really nice. And so Innsbruck, we also have a big physics department. So the city has a big medicine department and physics department, and also a huge experimental physics department. And in our group, we are a specialist in this kind of system. This is like what we call an ion trap. And so basically, this is how our string of ions look. So I know that most of you are more used to cold atoms, right? So the main difference between the cold atoms and the ions, as much as I understand, is that the ions, you can trap them for a very long time. So once you trap it, it stays there in the trap, and then you can excite it and play with your ions. I managed once I was doing measurements and I kept the same ion for about a month or more in the weekends it was without the lasers or anything, and it stays there. So this is a bit different. And I know the atoms you have to load every time, right? As far as I understand. Okay. Yeah, so this is a bit the outlook of the talk. So as I mentioned, I'm going to start very basic. I have the feeling most of you know all of this, but it's just to put the vocabulary a bit, to put it in the same frame and link it to the quantum computation and quantum simulation. So I'm going to start with what is a quantum computer. So the idea is to give the building blocks of both quantum computation and simulation. Once I do that, my idea is then to present the platform of trapped ions. So how we do this quantum computation with the trapped ions, how we use them, so how we control the electronic and the motional state to do the qubits, and how we use this to do gates and tune interactions. I would like then to show you photos of the experimental setup in our group. So I purposely took from different experiments. So our group is quite big. We are about 55 people now, and there's about 11 to 12 experiments. So it's all the things you can do with a trapped ion, basically. So my idea was to show you the different kind of setups that we have so that you get an idea of all the things that can be done. Then I'm going to present a bit more specifically the different projects that are in our group. Again, it's more to show you all the limitations and all the ideas and all the different lines of research that are possible with trapped ions. I'm going to present this a bit with some publications. And if I have time, I can present you some of the results from my PhD, which is more linked to this precision and accuracy business that you are. Okay? And so what is a quantum computer? So I'm going to refer to classical computers, to the usual computers that we have, so the laptops and the usual things that we do. And this is how one of the most recent quantum computers look like. So this is one of the setups that we have. I'm going to talk about this a bit later. But then basically the main difference between a classical computer and a quantum computer is that a classic computer is in one state at the time, while a quantum computer can be in many states at the time. And what do I mean by this? So if we have a classical computer, we operate, most of you know, with bits, right? So we have zeros and ones, so on and off, right? And the thing is, when we set our bits, each bit is completely independent from each other, right? So if I set 1 in 1, the other 0, 1, and all of this to make my algorithms, they are all independent. How this works with a quantum computer? What we have is qubits. So we visualize them with this sphere. So this is like the Bloch sphere, and we have a little vector here. And yeah, and so basically, we have the same concept of the bits that we have an down and up state, or 0 and 1 state. And this little vector are going to point out to my state, the state of my qubit. But the difference is the qubits, they live in the quantum world. So that means that they follow these quantum rules that probably most of you know, but I'm going to reintroduce them to show you how this is applied for the qubits. So basically, we have superposition, entanglement, and interference. And this makes that the qubits are actually in a combined state together. Yeah. And since they follow these rules, they can be in many states at the time. So by now, you can already see what is the advantage of a quantum computer versus a classical computer. It's just the capability to have many, many states at the time, which you can imagine if you're writing an algorithm, this allows you to have more power and solve some problems faster. So the idea is we don't intend in any point to replace classical computers with quantum computers, but we want to use quantum computers to solve problems that a classical computer will take too long or will require a very costly equipment. Yeah. So now to go through this concept for superposition. So the direction that my arrow points, so the way I prepare my qubit, is gonna give me the probability that my qubit, when I measure it, is gonna be in a given state. So this is the famous Schrödinger cat, right? That is dead or alive, right? And when we open the box, we see if it's dead or if it's alive. And so the qubit, we can prepare it in such a way that every time we measure, if we measure many, 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 many times, we have a 15% chance to be up and 85% to be down. Yeah. And this I can control it and have the opposite, for example. And so basically, I have a probability that it is in a given state. Okay. Once I have this, I can have also, with my qubits, I can have entanglement. So if they're not entangled, I have each one of the qubits has a different probability to be in a state or the other. But if I then entangle them, I will have a state, their state is going to be combined. And so they're going to have a combined state together that is interdependent. Yeah. So the way that this arrow points out is going to affect, so the way that each qubit is prepared is going to affect the whole state of the system. And this gives me also a set of states here, right? So I have a distribution of states, so that it can be that both of my qubits are in 0, 0, that the one in the left is in 0 and the one in the right in 1, or the opposite, or both in one. And then I have a probability distribution of all of these states. And when it gets interesting is depending on the number of qubits that I have. See, if I have n qubits, the number of states that I have is 2 to the power of n. Yeah. And this here, you can start to see how we have all of this capability to have many states at a time. Okay. And now, how can we control this probability distribution? The way we do it is that we take advantage of another property of the quantum world, which is a quantum wave function. Yeah, so we use this to visualize, but actually our qubits are a wave function, right? And so that means that they follow wave properties. And so if I entangle now my qubits, their wave function is going to be added together following destructive and constructive interference, right? So if they have the same phase, they are added. If they have opposite phase, they cancel. And so I can tailor my waves in such a way to have the probability distribution that I want, right? And this is basically how you can make a quantum algorithm, right? So by playing with these different quantum properties on the qubits, you can make the quantum algorithms that allow you to solve complex problems. Yeah. So one of the most famous problems, quantum algorithms. So there's many, but the most famous one, I don't know if you heard about it, is the short factorization, right? So it is this factorization that says that you can, in the quantum world, you can factorize a faster number with many digits, right? And this becomes important because it's basically how you can do decoding of different secret passwords or decode any kind of secret message, right? And so the idea I want to point out again is that the quantum algorithm is used to solve problems faster and more efficiently than with classical computers. So the important is to look at is to use complexity theory and see how much harder is it to solve the problem as the problem gets larger. That's where the quantum computer gets interesting, right? To solve problems that otherwise is too costly to do in the classical computer. Okay, so just to give you an example, to factorize a number with n digits, how hard it is. So the best classical algorithm so far, and this doesn't mean that someone can come up with a very clever idea of how to solve this to a better classical algorithm, but so far, the only one that is known, well, the best one that is known, scales 2 to the power of n divided by 2. And if we use Shor's algorithm, it goes log n, so polynomial. So that means it's way less costly to use a quantum computer to solve these kind of problems than with a classical computer. It doesn't mean a classical computer cannot do it. It's just that it's going to be faster and more efficient with a quantum computer. And here, another disclaimer, to run Shor's algorithm on a large number, you need about 1 million qubits. So they already know that they managed to reduce it a bit more to hundreds of thousands, but yeah, we are not there yet at all, right? So don't worry about your passwords. Don't go run into the bank or anything. But it's just, this is the thing that made people get interested in quantum computers, to start to look at these kind of problems that scale. Okay. The other interesting part about the same platform, but it's a bit different. It's quantum simulations. So this is an idea that came from Richard Feynman, and he said to use a highly controllable quantum system itself to make prediction about the behavior of other complex quantum systems. Now that we see it, it looks quite obvious, right? To understand the quantum world, what better way than to use quantum things, right? But what we usually do is that, when in physics mostly, is that we try to simulate all of these problems. But what happens when we try to simulate the quantum world? It gets quite complex, right? So even if classical computers can now simulate quantum problems, it becomes more and more costly when the problem gets more and more complex. So the idea is then to use a quantum system that I can control very well, that is more simple, to then create simulations inside of this system and then just observe them and then do the study. And this has very, very cool applications that can be used in real life for the development of, to study material properties or electronic properties, or to study chemical reactions, improving batteries, new chemicals, so on and so forth. There's many applications also linked to what we saw yesterday with machine learning. There's now even banks that are quite interested in trying to model complex economical systems and cybersecurity, among other things. Okay, and then, so as I mentioned, there's many platforms for quantum computation and quantum simulations at the moment. This is quite a famous one that is appearing, I don't know if you notice, in movies recently. So you see this kind of fancy candelabras appearing movies when they talk about quantum world, or I don't know, time traveling or whatever. And this is the usual superconducting setup. We have also linear optical quantum computer, color centers, neutral atoms, cavity quantum electrodynamics. But for today, if you have time, I have some slides where I can compare all of the different platforms. But I'm gonna focus today on a trapped ion quantum computer, so something based in ions. And this is, yeah, one of our most recent setups. Okay, so now I'm going to go to the second part. So far, any questions? It's all clear? Okay, so now we're going to look a bit more on how to use trapped ions to do all of these operations. So how does this work? Yes. So in this kind of setup, we have 16, but we have a group that has 100 in a linear string. And we have a 2D crystal now that is also on the order of 100. So the challenge now, so we can have, I'm going to show this a bit more in detail, but we can have the ions in the trap. That's not hard, right? The problem is to be able to control what all the ions are doing. So to properly address them and really be sure that there's no noise among them, and to have a full control, right? So having many ions is not so hard. You just send ablation pulses more, but the problem is then to address them and to have control over them. So at the moment, I think we are very, very good at working with 16 ions. We are okay-ish with 25. We are quite okay-ish at 50. And 100 is like the next step. And yeah, we are in some grants called Millennium, and the idea is to have 1,000. But I don't know if this is gonna go beyond the paper or the projects. Yeah, I think it will take some years before we can reach that. But I think 100 is the next milestone, I would say, that is coming in not too short time. Yeah. Okay. Yeah. So basically, in our group, we're specialists in calcium ions. We really like this ion, first because we've been doing it for, I think in our group for over 20 to 30 years. I think this is the time that since our group started, and we have already a quite mature hardware, and we can buy the lasers from Toptica. They're always helping us a lot. And it's quite easy to get all the different transitions that we need for the operations. And now we are quite good at setting new traps very fast. So when I joined the group, it will take like a year for an experiment to come from scratch to a setup. And lately, they started an experiment in January, and now they're already trapping ions. It's quite amazing how good they're getting at building the hardware really fast and getting all the system working. Yeah, so basically what we have is we load, but I'm going to explain a bit how we load, but we use calcium atoms that we ionize. The reason we ionize is that we want to have a charged particle because we want to trap it in an RF potential. So basically we have an RF potential where we can trap our calcium ion. And then once we have it trapped, or we have a string of ions, we want then to excite our qubit transition. For example, this is a narrow transition. Yeah. Because your trap is not necessarily homogeneous. So depending on the confinement that so I'm going to show it a bit later, but you have an RF field and also an end cap voltage. And so your potential is not fully uniform. So they spread to have the minimum energy. And so that's why they don't have the same separation. So the longer your string gets, the more separate they get in. Exactly. Yeah, it's quite harmonic still, but yeah, they spread to have the minimum energy in that harmonic potential. Yeah. Yeah. So we use a qubit transition. So it's a narrow transition here on the order of hertz of sub hertz. And basically we use another laser, another transition with a broadband to scatter many phonons. And we use this to cool and to detect our ions. And so basically to do our qubit transitions, we excite this here. And if the ion is in the upper level, then it's going to be dark, because when I shine this laser here, I don't have enough photons. And if it's in the lower level, then it's bright and I see many photons. So this is how we distinguish one state from the other. And the way we have it now in our setup is we are able to do what we call global excitation. That means we use one beam to excite the whole chain, but we can also have address beams, so we can control what we send to each one of the ions. Yeah. Yeah. You can tune it a bit as you want, depending on the potential that you have, but it's in the order of micrometers. Yeah. Yeah, you can. Yeah. And depending on how long your chain is, so you have, as I mentioned, an end cap voltage, so you can squeeze them. And at one point, if you squeeze too much, then they get 2D or in zigzag. But yeah, you can change it a bit. It could be depending on, I don't know, if you want to play with some kind of interaction to change, I don't know, the frequency at which they're oscillating. Yeah. Or to play a bit with the addressing or the coupling that you have. Yeah. Or if you want to load more, depending on how many ions you want to load, you usually change the confinement. Yeah. Yeah. So as I mentioned, so we have the electronic state that we excite with the ion, but we have also the motional state. So we have this potential where the ions are, and then we have this motional state. So the ions are oscillating in the trap at some secular mode, and then they can be either both in going all in the, we have a common motional mode, or a stretch mode where they go in different on opposite directions. And we have this in 3 directions. So we have radial modes and we have axial modes. The radial modes, we can decouple them by adding a DC voltage. Yeah. I'm going there in a second. Yeah. And so basically, yeah, to answer your question, well, both first, our ions, to be able to distinguish between the electronic and the motional state clearly, we need to cool down our ions. So we Doppler cool them and ground state cool them. So that means that they are ideally with 0 phonons. And then the nice thing is that we can couple these modes by shining, by using our 729 laser. So as you can see here, these are the electronic states, and this ladder here gives you the motional state. So this is if this means that I have 1 phonon in the lower state and this 1 phonon in the excited state. And I can resolve these transitions really nicely with my laser. And then I can couple my electronic state with my motional state. And I can play with this. And this is actually how we're going to do the entanglement. I'm going to show you in a second. I don't know that. No, I think it's not James Cobb. No. Yeah. Resolve Seidman. Motion. Yeah. Yeah. So basically, you can add or subtract phonons from your system in a very controlled way. Yeah. Is this clear so far? Okay. And basically, this is how we do what we call gates. So these gates is how we control our qubits to then do the circuits to do the quantum simulations. And so basically, we can have single qubit operations where we have our block vector here that's going to give us the state, the probability of to be in an up or down state. And we can rotate this in around the Z, the X, or the Y by following these Pauli rotations, right? And we do this by changing either the frequency, the phase, or the pulse length duration of our transition. And this allows us to have a full control of our single qubit operations. Yeah. Now, to do the spin-spin interaction, or basically to untangle both our electronic states, what we do is we can shine, if we shine the red and blue detune laser, so if we shine these two in two different ions simultaneously, what we are doing is, if we have two ions, we couple one ion to the motional state and we couple another ion to the motional state, and they're sharing the same, we do it with the same motional state. That means that through this, we are coupling their electronic state. And this is what creates basically the MS gate, or the entanglement between our ions. And this is another of the building blocks to make these quantum algorithms. Yeah. And so basically, this is how the basic elements from a circuit look like. So it's all the kind of operations that you can do to then solve your algorithms. Yeah. And so basically, the work is then to, yeah, you can play around in classical computers to try to figure out which kind of algorithms you want to run, and then you try to test them in the lab. Yeah. Okay. Now to look at how we do the quantum simulations. So if you think now multiple ions, you're going to have many modes. And so as I mentioned, we have the center of mass and the stretch modes. So it's like a forest of these modes. And what we do to do something similar to what was presented yesterday, we want to, for example, do the Ising interaction, right? So the way we do it is similar to the entangling gate that I showed you before. But what we do is we shine a red and a blue detune laser from the forest of modes. And this allows me to create this Ising interaction. And I can control the strength of my interaction between my qubits by changing, for example, this is the coupling, so the laser intensity. By changing the detuning that I have here, I can even add a different detuning here and make it a bit more sophisticated. And here is where I play a bit with the mode properties. So this is where it gets interesting to maybe change the confinement, because this is going to change a bit the oscillation frequency of your ions. And with this, then you create this Ising interaction in a controllable way. So, yeah. A nice experiment. You can basically do as you want. So you can do in pairs, you can do the whole string. Yeah, you could do it also with the global. No, you will do it with the address beam to do two ions. Yeah, but you could also, there's other kind of gates I didn't present it here, where you use the global and then entangle the whole system and create what we call a G at Z and system, basically. You can basically do whatever you want with this kind of, and there's more complex interactions. These are like building blocks, but then you can play with the addressed, you can play with the global, you can then play with both together. Yeah. Yeah. To control each ion. So by means of this addressing beam. So I have a beam that goes, I have two kinds of beams, one that goes to all of the ions and another one where I'm just pointing the beam to exactly one ion. And we do this, are you asking about the hardware or this is the question? We have AODs that we can tune the frequency of the beams in each one of the AODs and then go directly to each single ion. Yeah, that's why it gets challenging with 100. Yeah. There's different ideas of how to make this work with some diffraction crystals that will go in different directions. But yeah, this is the hardware that is being developed right now. And this addressing is quite challenging because you want to be sure that you are only addressing a single ion and that you don't have any coupling with the neighboring ion. So what we call crosstalk. And this is a pain. So I had to align this with the colleague, and it takes like 1 week of playing around with servo motors that change the position very slowly and change the length and the position so that you're sure that you have the minimum cross-talking. So this will be extremely cool if we can come up with some kind of machine learning or something to train some hardware to really tune down this addressing, because it's really a problem. If this gets messed up in the experiment, you really have to spend a long time tuning it. Yeah. So every time, this is the last thing we change if we have to change something. We really don't want to touch the addressing. Yeah. And there's a lot of research now going on. I think we had some collaborations with Fraunhofer to try to come up with some nice addressing setup. And I think with some company Infineon in Villa, also there's a lot of collaboration with with companies to try to help us to solve this, because this is like one of the things that is going to be very important once you have 100, especially if you want 1000. Yeah. Okay. So to come back to this easing interaction, so you can create to tune by changing the power of your laser and the tuning and all of this. Then you can change the interaction as a function of the distance, the different interaction you have for the separation of these different between ions. And you can do, they did this experiment, I think, in 2014, so a long time ago. But basically, the idea is that we'll create this easing interaction, and then they will put all the ions, let's say, spin down, and then they will flip one in the center, and then they will see how the interaction propagates along the ion chain over time. And then they can change a bit the strength of to tune a bit the interaction range, and they start to see this behavior. And this is really a quantum behavior. So using a quantum system that we can control, then we can start studying this quantum behavior. And this is where quantum simulation gets quite interesting. Okay. And this is how the big labs, so the original labs look like. So for the experimentalists that you're probably used to see this kind of labs. So we have, this is one of the older labs at the moment, where the setup is still in these optical tables. And so the tables are mostly for optics. And on top of, you can see all the electronics that control. We use for our setups acoustic optical modulators. Probably if you're experimenters, you're more familiar with it. But the idea is that with this, we can tune the frequency of our lasers. We can also control the pulse length. We can control the intensity that we send to the ion. So we have here the whole setup. And here in the center, we have a mu metal shielding. So our experiments are quite sensitive to the environment, so to magnetic field, electric fields. So to shield them from the magnetic fields, we have this mu metal shield, and inside of here, we have the vacuum chamber. So our system, they need to be in vacuum because you don't want any interactions with the environment as much as possible. So we have conditions of 10 to the minus 11 millibar. Okay. And just to show you, this is inside of the shield. This is from another setup. So, but basically the traps, the chambers, they look quite similar. So as you can see here, this is the chamber. Here I have the helical resonator that allows me to control the RF, or to keep the RF constant in the blades that I'm going to show soon. We also have, we applied on purpose a magnetic field to have a quantization axis. And so for this, we have, originally we were using coils, but lately we've been using permanent magnets to have this quantization axis. In the past, we were using ovens to load our ions, but recently we are using ablation targets. So we have a target of the species we want to load, and we shine a very energetic green pulse to create the cloud of atoms, and then ionize them in the center of the trap. And yeah, as you can see here, the rest is mostly optics. This is another one of the setups, is one that someone was talking yesterday. This is the one where they have the 2D crystal trap that I'm going to show soon. Okay, but before I'm going to show, this is it's called the Innsbruck trap a bit. Is a 3D trap, or the blade trap. So we have in these 2 pairs of blades, we put an RF field, and in the end caps, we put a DC field, and this creates this harmonic potential where we can trap our ions. So as I mentioned, we have a target where we can create a cloud of atoms, and we ionize them in the center. To detect them, the fluorescence, when we shine in the different lasers, we have PMT or MCCD cameras. And with this, we can distinguish if we are in the up or the lower state. Yeah. This is the 2D trap that someone was mentioning yesterday. I think you were mentioning. So it's very, the concept is is pretty much the same, except that for the 2D crystal, what you want is to have more access to different points of view of the crystal. So that's why the trap was designed in such a way where the electrodes for the RF and for the end caps are in such a configuration. And also because you need to have one of the radial modes very high and the other radial mode very low, which then gives you this 2D confinement. So basically, instead of having a chain, you then have this disk, right? And then the big challenge is to be able to have the hardware that allow you to sustain a big RF and to be able to work in such a, like this monolithic configuration. Yeah, I had the chance to be friends with the PhD student that is working with this. And then so I saw a bit how the whole evolution of the development of this trap, and it's quite amazing. It took like 4 or 5 years to finally reach this point, but now it's really working, and it's really cool how they can control basically even the structure of the crystal that they have. So the crystal, something that I didn't mention is, even if we have vacuum, we still have collisions with the environment, and this changes a bit the configuration every time. But now they have it in such a way that the camera detects which configuration it is, and then changes the RF, and then puts it back in the configuration that they want to be able to do the measurements. Yeah. The challenge now is so now they did some very cool measurements where they have some correlation spectroscopy to look at different shifts. So the evolution of the magnetic field through the 2D crystal. But now the big challenge is how to address each ion individually and really have a control of what each one is doing. And yeah, but this is like the next milestone, I would say. Maybe in the next 2 to 3 years, maybe they will reach this part. At the moment, they're still playing with this setup as it is and trying to get as much information as they can. Okay. Yeah, this is a bit how the laser setup used to look. This is just to show a bit the evolution of how the our labs are getting cleaner and cleaner and more efficient with time. And this is because as we are evolving, as the hardware evolves, the labs get more and more clean and efficient. So slowly, yeah, this looks so much nicer to work with and so much more compact, which makes it also robust. And to the point that now we have this kind of rack setup. So basically, in these 2 racks, we have the whole lab that I showed you before. So this is quite impressive. This started in 2020, and now they have the whole system. So the whole thing that we had in a full room is now all inside of these racks. So you have the control electronics, the laser controller, the fiber distribution and switching, stabilization, the 729, which is this narrow transition, the PC, even the one that we use to do the analysis and everything, it's here. The wave meter, you have here to control the trap DC and the trap RF. Here you have the AOM amplifiers, and here inside is the trap module. So basically a full lab is now inside of a rack. This is done in collaboration also with a company that is a spin-off of our group, which is AQT, Alpine Quantum Technologies. So basically the drawer that I showed you before now got reduced to the size of this drawer. So we have here all the lenses and mirrors and the fibers that then will go to the setup. And the idea is that in principle, you should never have to touch any of these optics. So once they are in the box, they're designed in such a way that you should not touch it. It's still in development, and we're still working out what is the best way to do this, because if you have experience with experimental physics, the shorter the distance between your mirrors and your lenses gets, the more difficult it is to do coupling, right? So to coupling the light here is quite challenging, and also all the mirrors are quite small. They're 1/2 inch, and so you have to really spend time coupling it back. But usually once it is coupled and everything is inside, we don't have to look at it ever again, unless we want to change something in the hardware. This is some module that was also developed. The idea is to have these double pass units. So you have everything in a little box, and then you just plug your fibers, and immediately you have your double pass. So that means that the light passes twice to the crystal, and then you can control the frequency, the intensity, and everything. Wait, did I skip one? No. Okay, here, and in these drawers, I show you, I told you this is where the trap is. So the trap that I showed you before is now lying here. Here's the helical resonator. Here's where the camera is, and all the detection, and all the addressing unit that I mentioned before is located around here. And this is all in this drawer, and that is already the mu metal shielding. Yeah. Sorry? Because, yeah, I'm putting it in one, then it's either too high or making more wide. I think you have, the idea was to make it as small as possible, and yeah, but it's easy to move 2 than to move a big one. Yeah, I would say, I'm trying to think why they thought it like this. I was not involved in the design. Yeah. I would say so. I think as you mentioned, also it's standardized. So it's things that now also I think they've been developed by Toptica and also by the wave meter, that all of these systems are now, they're slowly migrating more and more towards this kind of racks. But I know, for example, the in Japan, they have these clocks, strontium clocks that are in racks, and they look a bit different. I think for their case, they have 3 modulos because they want to be able to transport them. And I also, well, I can understand why the Japanese do it, because they have a bit my size. And so, for example, this is very convenient for a tall German person or Austrian. But for me, I need a little bench to go up and find the things. So you still want to be able to control it somehow in an easy way. And you want to be able to control the temperature also and the vibrations. And I think this gets easier the smaller you can make it. So they try to optimize it in such a way. That's a bit my intuition after working with it a bit. Yeah, and also, I mean, I had experience that another friend, she's working in the Alpine Quantum Technologies company, and she had to move her racks, and they're quite heavy. So she didn't do it herself, of course, but she had to hire a company. And so if I imagine that if you put it both together, it gets even heavier. So you want to have it somehow modular, but yeah. So that's why you want to make it as small as possible. Yeah, more flexible as possible. But I think this is still in development. It could change a bit the shape or not. Yeah, it's an interesting challenge. Is working on engineer and physics. Yeah. Yeah, and this is the trap that is now inside. So it's a similar one that I I showed you before. Yeah, and basically the thing that is still taking a lot of space is the experimental control. So in order to control these racks, we have what we call pulse boxes, where we can send different pulses to all of these AOMs, and to control these pulse boxes and to see what the ions are doing, we still need these classical computers to extract all of the information and, yeah, basically do the readout. And then there's a lot of effort in our group and also in this AQT company to develop the software necessary to do all of these operations, which is also a massive challenge. It's a lot of software writing and, yeah, to be able to control the hardware and at the same time to make it user-friendly. And, well, we're all physicists and we know that we're not the best at keeping our codes clean. So they try to make it like as clean as possible, as easy to use as possible. And yeah, so there's a lot of work in that direction. Yes, oof, and I almost out of time. Yeah, so now I'm going to present a bit some of the projects in our group. So I managed to put everything in these 5 topics, I will say. So we have, these are like the different lines of research that our group has. So there is quantum computation, fault tolerant, and quantum error correction. So the groups in the experiments in our group that are focused on this, basically they work designing algorithms that allows us to correct and predict for noise, and also to create algorithms that are tolerant to this noise. So even if we have a lot of control right now of what the ions are doing, they're still affected by noise and also by intrinsic quantum noise. That means that when you run these quantum algorithms, you're going to have errors. And then the only way to be sure that these are reliable is that if you can detect them, correct them, and also to be able to control them, right? And this you can do it by making your hardware as much better and better and better, but you can also do it by playing tricks with your quantum algorithms. So to use different ions in the ion chain and use some of them to detect errors, some others for calculations. And there's a lot of effort. I think in all quantum computation platforms, this is one of the milestones, to be able to control the errors up to a point that we achieve what we call very high fidelities in our measurements. And yeah, so basically these are one of the latest publications that are related to this. So yeah, they're all creating different algorithms to solve these problems and different techniques to predict these errors in the chains. Okay, then we have what I mentioned before, but I show you more of this, is what is new traps and hardware design. And so the other challenge, as I mentioned with the Shor algorithm, is that we need to have many, many, many qubits, which is one of the biggest difficulty for quantum computation is scalability. So to have the possibility to have more qubits, and the more qubits you have, the more noise you have, and the more difficult it is to control your system. And so there's a lot of effort in developing the hardware to solve these problems and to also reduce the noise and optimize operation and explore new physics frontiers. So yeah, as I mentioned, there's this 2D crystal setup and that now can have up to 100 ions. And yeah, and this I already talked a bit. And then there's other kind of setups that instead of using these these 3D traps, they have surface traps. But this comes with the problem that the ion is closer to the surface, which means that there's more sensitive to heat that comes from the surface. And this system then need to be put in cryostats. So the idea is to create these traps that are like sorry, this is a hard one in English, chips. And then you can store your ions in different parts of your chip. But the problem is that you are more affected by heating. So these traps, they need to be then put in cryostat systems, which is another big challenge. And you have to be able to control all of your electrodes and play with it. So another of the experiments in our group is there are like 2 big projects. They're working then with this type of traps. You can see it a bit here, and it's all inside of a cryostat system. And they are playing now, they're able to rotate their ions and shuffle them around a bit at a wheel, which is kind of cool. Okay. There's also this work in making the hardware more and more compact. Then there is work in quantum simulations. So as I mentioned before, is to study complex systems using the trapped ions. And so there is this kind of project similar to what I showed you before, where they want to look at emerging hydrodynamics in a long-range quantum magnet. So they created this easy interaction a bit at a distance, and they start to see this hydrodynamics in the system. Or there was also this really nice paper where they were trying to understand a bit how photosynthesis works. So in photosynthesis, the light is harvested in a very efficient way, and nobody really knows why it's so efficient. And so one of the ideas was that is probably because it's somehow assisted by the environment. So what they did is to add a bit of noise in the chain to simulate a bit this environmental assisted, this environment that assists the transport. And then they were creating these interactions to see how the information, the energy is distributed in the chain. And then they saw that depending on the noise that you have, this becomes more efficient. And then there is one of these latest kind of experiments, which they use variational quantum systems. And this is a mix between a classical computer and a quantum computer. So it's as if your quantum computer was actually like a graphic card that you were using to do quantum simulation. So basically you link both, you prepare your Hamiltonian in your quantum computer, you get some measurements, and then they are feedback into the classical computer, who is trying to minimize this Hamiltonian, and then tells the quantum computer which parameters to change to search for this minimum. So you link both, and then you create like a tool to solve problems that is more efficient than just the quantum computer or just the classical computer, just to add and merge them both. And yeah, so they use this to study lattice gauge theories. Okay, this is more the precision and fundamental physics that you are more familiarized. So it's exploring new species to do quantum sensors, or to explore different ways of studying fundamental physics. And finally, we have another set of people in our group working in distributed quantum system and quantum interfaces. So basically, we put ions in the center of these cavities, or we have also nanoparticles floating next to the ions. And then the idea is to explore interactions between light and matter and create quantum networks and quantum sensors. So the idea is to do this entanglement at a distance, so that we are able then to entangle different modes. And yeah, basically they managed to do this with a 50-kilometer optical fiber. In this experiment, they had the fiber in a bundle, and then it was going quite a far distance, but still not really 50 kilometers. It was the fiber that was 50 kilometers. And they're working now in really have 50 kilometers between two modes. But yeah, basically this is the kind of experiments. They also have the group of Tracy Northup. I don't know if you know, she has these levitated nanoparticles now, which opens a whole new realm of research in with quantum systems. And yeah, I think I'm a bit out of time, so I'm gonna skip the clock part. Yeah, so basically to sum up, then I hope I could explain to you what is a quantum computer, how you can do this with trapped ions, and what kind of projects you could do if you were interested in working with this kind of setups. I hope it's clear. Yeah, can answer some questions. Yeah.
Imaging your 2D trap.
Sorry?
For imaging.
Yeah.
Like what imaging do you use and how efficient it is for your 2D trap?
By my cooling rep?
Means when you're making the 2D plot for the
2D.
traps.
Okay.
So like what is the imaging system you are using?
We have also PMT and camera.
No, for the imaging of the ions.
Yeah, with the camera, CCD camera, and then you can see all the ions in the camera, basically.
Okay, for the 2D trap also you're using the EMCCD.
Yeah, correct. Yeah, we worked in some sort of, well, I didn't, but there was a team that developed this software that allows them to really identify where each ion is in the camera image, and they can even subtract the cross noise between the different ions. This is some work that Christian Ross worked with, and so basically they designed this software that allows them to detect what each individual ion is doing. So they take an image, and from this they create some grids where they can detect where each ion is in a reliable way. If they they need to first control that the crystal is always the same, because as I mentioned before, the crystal can change shapes. But if they keep the same configuration, they know exactly where each ion is, and then they read how many pixels they are per ion, and with this they do the imaging. Does that answer the question? Yeah.
Yes.
You mentioned that the highest qubit you guys build is 100?
100, yeah. I think 120 they managed with this 2D.
Okay.
But this is the usual thing they do for papers. They try to do the maximum.
You know how much fidelity?
No, for this crystal, there's no work on fidelity, yes, because we still are not working with gates yet. At the moment, they're controlling the crystal, and yeah, because it comes with other challenges, right? You also have micromotion, which is the noise that comes from the interaction with the RF, and yeah, and there's still a lot of things to solve before you get to do gates, and before you worried about fidelity with these 2D crystals. I think with the 100 ion chain, they're working now. Like there's also this chain. They're working now on the fidelities on that. I think it's the next PhD student, and that experiment is working more on that. But they're still working on the fidelity. They now can control like single qubit operations, so they can have each qubit control in a very precise way. But to tell you fidelities in gates, that's a different thing. For 16 ions, I think we are on the order of 90% fidelity for a G at Z state. So when you entangle them all with all, for a 2-qubit, so if you have a 2-qubit gate in the 16 ion chain, you have something on the order of 98 to 99. For ion for chains of 8 below, there's already up to 99.9. Yeah.
Is it already possible, basically, if you have like on these chip like 2 linear pole traps, that you entangle like these linear pole traps with each other?
That you entangle them?
No,
Yeah.
like I mean, like if you have on these chips, I guess what they want to do is like having more linear pole trap next to each other. Is there already a possibility to entangle like different linear pole traps with each other?
And they're playing with that right now. And so it's one of my friends, and he's working with this right now. So they have already 2 wells in the chip. And so basically what they're looking now is that if you have them, they already have 2 ions in each well, which is quite challenging already. And then they're moving them together and try to even create correlations by just pushing them together and see how they're interacting. So they're already playing there. To do a gate, it's still not a thing.
Okay, so they do it with motion instead of like having like this, as you said, like basically photons which are like out of a cavity and then store the entanglement information and then
Okay.
use the other one.
Yeah. This in a single chip only now. They're just starting. It's quite a challenging experiment to work with these chips. So I think they managed after many iterations, because it's one of these projects that starts very ambitious, and then they had these very complex chips with many electrodes and things, and then they figure out, okay, maybe we reduce all the electrodes, we make it simple and make it work, and once we have this, then we start building up. And now they managed to have one of these traps where they can have these 2 wells, and they're slowly playing to try to control them, but they are still affected by very strong heating rates that they have to understand, because then you have potentials that are interacting with each other, and it's a bit messy and complicated. But yeah, they're working there. It's quite exciting. It's quite a cool experiment. Yeah.
Are there any other questions? My question is, maybe stupid or naive, do you need many lasers for each ion, like 1 laser per each ion?
No, it's not stupid at all. No, it's a bit what he asked. So we have acoustic optic deflectors. So it's like a crystal that would change the position of your beam. So it's like a set of these AODs, we call them. It's a string, and then you can tune the position of your beam. So you use 1 single beam and you send it to these AODs, and then you can then tune them. But this is extremely challenging because, as I mentioned, you need to be able to, well, basically you're shining a beam to every single ion, and you want to be sure that they're not, you're not contaminating the other ones in the chain. Yeah. But we have different lasers, though, for different transitions, for example. And we do have sometimes, well, what we do is we use fibers, and we can split our beam to address different directions too. Yeah.
Okay, if there are no further questions.